Today we're going to start a new unit on exponential functions. We're going to talk about their graphs. We're eventually going to talk about applications, and we're also going to talk about logarithms. Today we'll focus on exponential functions and their graphs. So let's start with what an exponential function is. So an exponential function is a function where the variable is in the exponent. So for example, if we have y equals a to the x, and a is a constant, it's a number that's given, x is the variable, and it's in the exponent. We would call a the base, and the base a here has to be greater than 0, and a does not equal 1. Now if a is equal to 1, you end up with 1 to the x, and you know that 1 to any power is just going to be equal to 1. So we wouldn't call that an exponential function, just because of the way that graph behaves. Now the domain of all exponential functions is going to be all real numbers. So in other words, the values that you can plug in for x, you can plug in any real number for x. It can be positive, it can be 0, it can be negative. There are no restrictions on the domain. Let's take a look at example 1. We are going to go ahead and graph y equals 2 to the x and y equals 4 to the x. Before we get into the graphing portion, we're going to fill out a chart, plug in some numbers, and get some actual coordinate points in order to graph or sketch the graph of these functions. So let's start with y equals 2 to the x. So when you plug 0 in, 2 to the 0 is equal to 1. When you plug 1 in, 2 to the first is equal to 2. Plug 2 in, 2 squared is equal to 4. Let's plug in some negative numbers. So if we were to plug in 2 to the negative first, now 2 to the negative first is 1 over 2 to the first, which is 1/2. And then plug negative 2 in, you have 1 over 2 squared, and that would be 1/4. Okay, so plugging these points onto our graph, we have 0, 1, 1, 2, 2, 4, negative 1, 1/2, and then here you just have to be as close as you can, negative 2, 1/4. And that's the graph of the function y equals 2 to the x. Let's do the same thing with y equals 4 to the x. So plug in 0, 4 to the 0 is 1. Plug in 1, 4 to the first is 4. Plug in 2, 4 squared is 16. Plug in some negatives in there. So plug in negative 1, we have 1 over 4 to the first power, which is 1/4. Plug in negative 2. We have 1 over 4 squared, which is 1 over 16. So we'll just do our best graphing those. So 0, 1, same point there, 1, 4, 2, 16, that's going to be already off the graph. Okay, negative 1, 1/4, it's going to be down here. Negative 2, 1/16, that's even closer, but not yet touching. Do the best you can drawing that in. And that's the sketch of our graph y equals 4 to the x. So you will notice a couple things. One had a base of 2, one had a base of 4. The one with a base of 4 increased much faster as x went up, but it also decreased much faster as x went down. So that's really one thing to notice. Another thing to notice is that they actually have the same y-intercept, because anything to the 0 power is equal to 1. So 0, 1 is going to be the y-intercept in both cases. Let's take a look at what happens when the exponent is negative. Y equals 2 to the negative x. So plugging in 0, we have 2 to the 0, which is 1. Okay, plug in 1. So now we have 2 to the negative first. So that would be 1 over 2 to the first, which is 1/2. Plug 2 in, we have 2 to the negative second, which is 1 over 2 squared, which is 1/4. Plug in negative 1, we have 2 to the positive 1 now, so that's 2. Plug in negative 2, we have 2 to the positive 2, so 2 squared, which is 4. So now we can go ahead and graph these points onto the grid over here. So we have 0, 1. Let's do the ones without fractions first. So negative 1, 2, negative 2, 4, Okay, now let's deal with the fraction. So 1 1/2, 2 1/4. So here is what the graph looks like there. So you'll notice that when we have a negative in the exponent, that actually translates into what? It's a reflection in the y-axis. So just to summarize our two different graphs, so y equals a to the x, that's the one in red up there, and y equals a to the negative x, that's the one in blue. So the first one is an example of exponential growth. So as x increases, y also increases. Whereas the second one we would call exponential decay. So as x increases, y decreases. The domain for both is going to be all real numbers, right? You can plug in any value for x, positive or negative or 0. You can talk about the range of each of them. They're actually the same, right? In both cases, it never crosses the x-axis, it never goes under that. So it goes from 0 to infinity, not including 0. The y-intercept in both cases would be at 0, 1. In exponential growth, we would say this is an example of a graph that is continuously increasing. Remember, we're always talking about looking at it from left to right. So going from left to right, it is increasing. And for exponential decay, it would be decreasing as you move from left to right. In both cases, we already sort of talked about this when we talked about the range, but essentially it never ever touches 0, but it gets very, very close to it. So we would say it has a horizontal asymptote at y equals 0 in both. Okay, the next things we're going to write down, these are kind of getting us into calculus sort of notation, but it's good to start practicing them here. So reading this says the limit as x approaches infinity of a to the x. Okay, so the function that we're working with is a to the x. And we're saying as x goes to infinity, what is this going to go towards? This is going to go towards infinity, right? As x gets larger and larger, a to the x also gets larger and larger. And then as you're going in the other direction, as x approaches negative infinity, as x gets really, really small, what happens to the function? As x gets really, really small, the function gets very, very close to 0. Now with exponential decay, that's going to be just the opposite, right? So as x gets very, very large, this goes to 0, right? We're looking at that blue graph. As x gets very, very large, it gets closer and closer to 0. And then as x gets very, very small, so as you move towards the left, your function gets very, very large, goes to infinity. Okay, so let's talk about transformations of exponential functions. Now we've talked about different types of transformations and they apply to exponential functions just the same. So if you have a parent function, f of x equals a to the x, and here's the transformed function. So let's say we have all the different transformations in there. So a negative out in front versus a negative in the exponent, they're both reflections, but if it's out in front, it's in the x-axis. If it's in the exponent, it's in the y-axis. The plus or minus c is going to shift it left or right. Now remember, for left and right, if it's plus a number, it's going to shift to the left. If it's minus a number, it's going to shift to the right. And then the plus or minus d, that shifts it up or down. And this one is more natural. So plus d shifts it up, minus d shifts it down. Okay, so let's sketch graphs of these functions here. So the parent function here is 3 to the x. So what we're going to do is we are going to list what the transformations are, and then we'll go ahead and graph them. So 3 to the x plus 1, so the plus 1 is in the exponent, so that means it's a shift left or right. Because it's plus 1, it's going to be a shift to the left 1. Okay, so if we take our graph, I like using For 3 to the x, I like using 0, 1 for the parent function, a point that the parent function goes through, and then moving that around. So 0, 1 is now going to shift over to the left, and now it's going to be at negative 1, 1. Okay, for the next one we have 3 to the x minus 2. Because the minus 2 is not in the exponent, that indicates that this is going to be a shift up or down. In this case, it's going to shift down 2. So now again, I'm going to take that point that's normally at 0, 1, and I'm going to shift it down by 2. So now it's going to be at 0, negative 1, and then draw the graph in. Okay, the next one, negative 3 to the x. The negative is in front of the function, so that indicates it's a reflection in the x-axis. So I'm going to take that point 0, 1, I'm going to reflect it in the x-axis. Now you just want to make sure that you don't draw it the same way you did the last one, because the entire function has actually reflected, right? It's not just that we shifted the function down by 2. It's that the entire thing, you can think of it as just folding it over the x-axis. The last one, we have 3 to the negative x. The negative that's on the exponent now indicates that we have a reflection in the y-axis. So if we were to draw that now, 3 to the negative x, again, use that 0, 1 from the parent function, reflecting it in the y-axis. Well, it's on the y-axis already. So for this, if it helps, think of what the original parent function 3 to the x looks like, and then imagine folding it over, or folding it along, the y-axis. So now our graph should look something like this. Okay, so we've talked about exponential functions, we've talked about exponential growth and decay, and the different transformations. Now we're going to talk about the natural base. So the natural base is e, and e is similar to pi in that it's what we call an irrational constant. So there is a very specific value to it, right? It's a constant. It's not a variable, but it is irrational. Irrational meaning that it is not a value that can be expressed as a ratio of 2 integers. So the value of e is about 2.718. And again, this continues on and on just like pi does, but normally when we use pi, we don't use all of its an infinite number of digits to calculate. In fact, you probably have shortened it to 3.14 at some point in the past. With e, it's good to use 2.718, like 3 decimal places is probably good. But on your calculators, you also have the e button, just like you have the pi button on the calculator. So the natural exponential function would be y equals e to the x. So instead of something else being the base, like 3 to the x, 2 to the x, now e is going to be the base, so e to the x. The domain, just like with all the other exponential functions we've seen so far, the domain is going to be all real numbers. The range goes from 0 to infinity. Again, it gets very, very close to, but never actually reaches 0. Y-intercept is still at 0, 1. And because this is e to the x, not to the negative x, this is going to be increasing as you go from left to right, with a horizontal asymptote at y equals 0. And you could say, because this is an exponential growth type problem, that as x approaches infinity, e to the x goes to infinity as well. And then as x approaches negative infinity, as it gets very, very small, e to the x gets very, very close to 0. And so here is our function y equals e to the x. So notice 0, 1 is still the y-intercept. And then e to the first would be about 2.7 or so, right? So when you graph that, make sure that you use that to help you. Okay, now using the natural base e, we can use this to model exponential growth. So here is what we call the PERT equation. A equals P times E to the RT. A is the amount or a future amount after some time t has passed. P is the principal amount. So this is what we consider the original amount that you start with. Now the rate R is expressed as a decimal. If you're working with exponential growth, then the rate will be positive. If you're working with exponential decay, then R will be negative. Now you'll notice that means if you're looking at the equation, if R is positive, then you have exponential growth. If R is negative, then you have exponential decay, which is what we saw earlier today. And then t is the time. It can be in years, it's often in years, but you just want to make sure that the rate and the time correspond with each other. So if the rate is given as, a lot of the times it'll be a rate per year, it increases at this per year, then you want to make sure the time is in years. On the off chance that you might be working with something like this grows at this percent per day, then you want to make sure that your t time is also in days. Okay, let's take a look at an example together. Let y represent the mass of a quantity of radioactive element whose half-life is 25 years. After t years, the mass is given by this formula. So this one actually gives you a formula to use. Part A, what is the initial mass? And part B, how much of the initial mass is left after 80 years? Okay, so this is what we call a half-life problem. And when you're told what the half-life is, what that really means is that's the amount of time it takes for the amount of mass that you start with to go down to half. So let's say you started off with 100 grams. Then, after 25 years, you will have 50 grams. All right, so that's what half-life means. Now, what is the initial mass in this problem? Well, the initial mass is when t is equal to 0, when no time has passed. So if we plug 0 in for t, we end up with 10 times 0.5 to the 0 power. Now, make sure that you deal with the exponent first before you multiply. So 0.5 to the 0 is equal to 1, and then 10 times 1 is equal to 10. So initially, we were starting with 10 grams of this radioactive element. Part B, how much of the initial mass is left after 80 years? Well, we're working with 80 years, so after 80 years have passed, so t equals 80. So if we plug in 80 for t, and again, you want to make sure that you are raising 0.5 to the 80 over 25 first before you multiply by 10. So don't do the multiplication first, right? Rules of PEMDAS still apply. Exponents first, then multiplication. So this, if you were to do this out, this comes out to be about 1.088 grams. Now, if you want to have an idea of how accurate that is, or if that's even ballpark in the right place, you can absolutely think about it as, okay, we start with 10 grams. I know after 25 years, I'm only going to have 5 grams left. After another 25 years, I'll only have 2.5 grams left. And after another 25 years, I'll have a little bit more than 1 gram left, and that will be after 25 plus 25 plus 25 years. So that's 75 years. So this is approximately right, in ballpark in the right place. So that's how you can think about half-life and about approximately how much you should have left, and you can see how this is an exponential function.